All right, so we have been talking about how heat is transferred from a hot object to a colder object, and we said that there are three mechanisms for which heat can be transferred: conduction, radiation, conduction, convection, and radiation. And in our lecture yesterday, we talked about conduction and convection. So today we will wrap up the heat transfer mechanisms by talking about radiation. As usual, heat is transferred because of a difference in temperature, and the direction of heat flow is from high temperature to low temperature objects. Just to differentiate between the different mechanisms for heat transfer, yesterday we defined what conduction is, and the main feature of heat transfer by conduction is that heat is transferred through the collision of particles and atoms, and there is no movement of amongst the objects, but they do have to be in contact with each other. For convection, heat is transferred by the movement of particles. So this is more common in fluids like liquids or gases rather than inside the solid. So in both the conduction and convection heat transfer mechanisms, a medium is required. Of course, you need to have a material that has atoms and particles that will collide. For conduction and for convection, you need particles that will move and bring with them energy as they move. Whereas for radiation is energy transferred by electromagnetic waves. We will not really talk about electric fields or magnetic fields or waves, electromagnetic waves in this course. If you're taking 124105 in semester 2, that's when we will learn about waves and electromagnetic waves, electric fields and magnetic fields. But just for the purpose of heat transfer by radiation, essentially, if you have atoms consist of protons, positively charged particles, and electrons, negatively charged particles. And if protons and electrons move, like in the vibrating atom, they create electric fields and magnetic fields. And when electric fields and magnetic fields propagate, we call them electromagnetic waves. So the atoms containing the electrons and protons are, of course, inside the material. And it's through the propagation of these electromagnetic waves where energy is propagated from the material which contains the vibrating atoms to the environment or to different materials. And so heat transfer by radiation is the mechanism for which the heat from the sun is able to reach us on Earth, because electromagnetic waves can propagate through vacuum. So we don't need particles to carry energy with them as they move about, unlike convection. For electromagnetic waves, they can propagate through space, through empty space, through vacuum. And as they propagate, they bring with them energy. Now, going back to what I said earlier about electromagnetic waves that's generated by the movement of protons and electrons. Essentially, all matter, like all objects, consist of atoms, right? And inside these atoms, the electrons and protons are vibrating and therefore generating electromagnetic waves. Since all matter consists of atoms, therefore, all matter will emit thermal radiation, except, of course, when the object is at 0 Kelvin, the absolute zero temperature, where everything is frozen, all atoms are frozen, meaning they're stationary, they're not moving, then that's when this object is not emitting radiation. But to date, 0 Kelvin hasn't been achieved, not even in the lab. And so all matter will have these vibrating atoms and therefore electrons and protons that are moving, therefore creating radiation, thermal radiation. After all, we've been learning, right, that the movement of atoms is equal to temperature. So as long as you have vibrating atoms, there is some temperature in that object, and that temperature being propagated, the energy corresponding to that particular temperature being propagated is what we call the radiation. So yeah, so that's up to the point where we will talk about electromagnetic waves in this course. It's simply the means of propagating energy through vacuum. And the rate of radiation can be influenced by various factors. So like yesterday, when we talked about conduction, we looked at the different variables that affects how much energy is transferred by conduction, right? The area, the length over which heat is transferred by conduction, and all the other variables. So similarly, we will look at the different factors that affect how much energy is transferred by radiation. And the equation is given by Stefan Boltzmann law. But before we look at the equation, let's look at the various factors first. So one factor that affects how much energy is transferred by radiation is called emissivity, small e. Emissivity is a property of the material, just like thermal conductivity. Thermal conductivity, we learned yesterday, is a property of the material which tells you how effectively it can conduct heat. Emissivity is also a property of the material which tells us how effective the material can emit or absorb radiation. And since it's a property of the material, it will have some value, some fixed value, but E varies only from 0 to 1. Right, when will E be equal to 1? E will be equal to 1 if the object emits or absorbs all of the radiation. In other words, if the object is a perfect or ideal emitter, then E is equal to 1. And the perfect or ideal emitter is called a black body. So black body is just a term we use to say that the object is a perfect or ideal emitter. Incidentally, dark objects have emissivities close to 1, and hence the term black body. Black body just refers to a perfect emitter or absorber. Right, so yeah, so black and very dark objects, they have emissivity close to 1. So anecdotally, you might have heard, like, if you wear a dark T-shirt on a summer day, then you feel warmer compared to when you wear a white T-shirt, and that's because of the emissivity. I don't know if you've heard that. I've heard that. So yeah, so E is close to 1 for usually black and very dark objects. When is emissivity 0? This is when the object is highly reflective. So when the object is highly reflective, like shiny metals, they tend to reflect the radiation incident on them, and so they effectively do not absorb the radiation, and hence emissivity will be close to 0. Right. Cool. So radiation, the amount of heat transferred by radiation is also affected by area. And when we say area, it means the surface area that can absorb radiation or emit radiation. Yeah, and usually that's how, for example, animals who live in the desert, they usually have larger surface areas like this fox here will usually have larger ears. If you also compare elephants who live in Africa to elephants who live in Asia, for example, African elephants tend to have larger ears because then they will have more surface area to emit radiation, and that regulates their body temperature. Right. Okay, the amount of radiation also depends on the temperature of the objects. And that usually the hotter the object, the brighter it glows. And you can also think of this as the hotter the object, the more the atoms vibrate, and therefore the more radiation the object is able to emit. Yeah. All right, so far, are we okay with the concept of radiation, like how energy is being propagated or transferred through radiations? Before we look at the equation, so we have now looked at the different what's this? Quantities or parameters that affect the amount of radiation, like surface area, emissivity, and temperature. And we can combine all of these into a single equation called the Boltzmann equation, Boltzmann law. But before we do that, I'll just show you this rather cool video clip. So thermal cameras, they can image the amount of radiation emitted by certain objects. And the more radiation is emitted, the redder it appears in the thermal camera. And so the less radiation is emitted, the more bluish it looks like in the thermal camera. So just have a watch this video. And hopefully,
hello and welcome to Earth Unplugged.
The sound doesn't seem to. Right. So in reality, we don't really exist in isolation. So as I mentioned earlier, I'm emitting radiation at the same time. You are emitting radiation and I'm absorbing the radiation you're emitting. So if we consider the surroundings of the object, then the amount of heat loss will also depend on how much our surroundings emit radiation, right? So the total amount of heat transferred by radiation will be equal to the heat absorbed from the surroundings. So how much radiation, how much energy I absorb from the radiation you're emitting, minus the amount of energy that I emit via radiation. So it's a combination of radiation absorbed from the surroundings and radiation that I give off to the surroundings. Of course, it makes sense that the heat radiated will have this negative sign, because as I radiate heat, I lose energy, and the heat I absorb will let me gain energy. So the heat absorbed will be the positive heat, and the heat that's radiated will be the negative heat. So if we combine this, the heat absorbed from the surroundings will also be given by Stefan's law. And at the same time, the heat radiated will also be given by Stefan's law. I did a little bit of simplification here now, but if you want the non-simplified version, that's S. Yeah, it's exactly the form of Stefan Boltzmann's law. Yeah, just distribute T there. Emissivity, sigma A, and the time, they are all appearing in both equations. So we can factor them out, and hence we have outside the bracket here, emissivity times sigma, Stefan Boltzmann constant, times the area and times the time, because they appear on both sides of, on both terms of this equation here. Right, so the meaning for each terms are written down here. It's the same meaning as when the object is isolated. There is just an additional temperature from the surroundings. But again, I emphasize that the temperatures, they are raised to the power of 4. So although you are subtracting temperatures here, you're not really taking delta T in the sense that it's cold temperature, hot temperature minus cold temperature. Rather, you are taking the difference of temperature raised to the power of 4. So hence, the temperatures really have to be in kelvins to match the unit in the constant, Stefan Boltzmann constant. All right. Okay, so any questions so far for this equation? Then let's look at an example of how we apply this. Oh yeah, before the example, again, the rates, just as usual, if you want to find the rates, then that's the amount of heat divided by the time. Everything else will be the same, except that the time factor goes to the other side of the equation here. And as I've always been emphasizing, even for heat transfer by conduction and convection, when the temperature of the objects is equal to the temperature of the surroundings, heat transfer stops, even by heat transfer by radiation. All right, now the example. So you have a person whose total surface area is 1.5 meters squared. And this person is in a room. The room's temperature is 22 degrees Celsius. And the temperature of the skin is 33 degrees Celsius. The emissivity of the skin, let's just assume it to be 1. So it's a very dark-skinned person in this case. So how much, it's the rate is Q over T, or how much energy is radiated per second by this person. If you want the equation, so the person is in a room, and therefore you need to consider the environment or the surroundings, and the radiation that is absorbed by this person from the surroundings, as well as the radiation that this person emits. Right, so TS, that will be surroundings. Just the T means the object that's radiating. Again, The temperatures are given in Celsius, but you have to convert your temperatures to Kelvin. So you cannot get away with just degrees Celsius is equal to Kelvin. You really have to convert your temperatures to Kelvin. Okay, and assuming you've done the conversion, that's adding 273 to the Celsius temperature. Don't forget to raise the temperatures to the exponent 4. Emissivity is equal to 1. The constant, 5.7 times 10 to the minus 8. Right. That's T to the 4. Surroundings to the 4, and then the area, 1.5 meters squared. So every second, the person, it's a positive number. So this is the person. Right? Okay, any question about this example or how to use the radiation Stefan-Boltzmann equation? Right? Good. Okay, right. So now we have seen and we have learned the 3 mechanisms for heat transfer. There is one special case called evaporation, which is also sort of a means of changing the temperature of an object. And I discuss evaporation because it's quite unique. So in evaporation, usually sweat. Let's just consider a person that's sweating, but it doesn't have to be sweat. It can be, for example, saliva from the dog's tongue evaporates into the atmosphere, resulting to a change in temperature. But in essence, what happens in evaporation is you have some liquid that evaporates into gas, hence this term here. And as a result of the liquid evaporating, you have a change in temperature. So in evaporation, you have this ml is equal to mc delta T. Let's just look at what each term means. So ml, this comes from Q is equal to m times latent heat of vaporization, LV. What this equation essentially means is some heat Q is needed to evaporate the liquid, and hence you have this latent heat of vaporization. So this is heat needed to evaporate. And therefore, the mass here will be the mass of the liquid that evaporates. Right, so heat is needed to evaporate the liquid. Where will that heat come from? It will come from the body. And as a result of the body losing heat to evaporation, the temperature will change. So this mc delta T on the other side of the equation is the Q equals mc delta T. It's the heat heat that goes into evaporation. And because you're losing heat, that results to a change in temperature, resulting to a change in temperature. Okay, so since the Q equals mc delta T refers to a change in temperature of the object or the body, the M in this mc delta T therefore refers to the mass of the object whose temperature will change. whose temperature will change. Right? So in other words, when sweat evaporates, the temperature of the object will change in essence. And that's why we cannot cancel masses in the opposite sides of the equal sign here, because the masses mean different things. The mass in MLV means it's the mass of the liquid that evaporates, and therefore uses this amount of heat, whereas the mass in MC delta T refers to the mass of the object whose temperature changes. So we're looking at two different masses here, and therefore these masses don't cancel each other out. Okay, all right, so let's look at this example, how to apply, how evaporation cools down the body. The latent heat of vaporization is given here at body temperature. So sweat is mostly made up of water, and the latent heat of vaporization of water is given here. 75 kilogram jogger has a specific heat. The body of the jogger has a specific heat of 3,500 joules per kilogram per degree Celsius. And we want to know how much water, or how in the form of sweat, needs to be evaporated so that the temperature of the jogger decreases by 1.5 degrees Celsius. Right, so there are two different objects or things here in this problem, right? We have the jogger, who has a mass of 75 kg. Okay, the jogger needs to change its temperature by 1.5 degrees Celsius, needs to lose heat in order for its temperature to decrease by 1.5 degrees Celsius. Since we're getting a change in temperature, we can also say that that's 1.5 Kelvin. We're given the specific heat of the body. Okay, so the jogger needs to lower its temperature. That means he needs to lose heat. The lost heat goes into evaporating sweat. The latent heat of vaporization for the sweat is given 10 to the 6 joules per kilogram. And what we want to find is how much sweat needs to be evaporated in order to achieve this change in temperature, 1.5 degrees Celsius. All right. So is the problem clear, and how we have assigned the values? So you can see here now that the jogger needs to lose heat to lower its temperature. Where will that lost heat go? The lost heat from the jogger's body will go into evaporating the sweat, and therefore you have the heat needed to evaporate the sweat will be mass of the sweat times latent heat of vaporization of sweat, and that heat used to evaporate the sweat will come from the heat lost from the jogger. Mass of the jogger times specific heat times the change in temperature of the jogger. And we're after how much sweat is evaporated. And we have everything we need. So it's now just a matter of substituting the values. And 0.163 kilograms. Any question about this question or yeah, how we solve evaporation? So in a way, evaporation can be thought of as a special kind of heat transfer mechanism, because heat is transferred from the body to make the sweat evaporate. But so any question about radiation or any of the heat transfer mechanisms for that matter? I hope it was easy enough to follow. Good. All right. This is why this is one of my favorite topics. Yeah. No, because as the electromagnetic waves propagate, their energy is sort of preserved. And so the amount of energy they carry from, for example, from the sun to the earth will be the same. Okay. Then
and it's closer to the sun, a hotter than further away. But radiation doesn't produce over distance. So.
Yeah, that's a good question. I haven't thought about it.
Mercury doesn't have an atmosphere, right?
Yeah.
It's to do with the angle of the light. So Mercury is smaller because it's closer to a wider angle of light, whereas because the Earth's further away, it's a smaller angle of light.
Right. So it is the surface area then. So you can see if you have like a wider with radius. Yeah, that makes sense. Yeah, it is not the actual, but the energy is still the same. All right, good. Then that wraps up our discussion on heat transfer. In the next lecture, we will now look into thermodynamics itself. But you do have the workshop tomorrow. So I'll see you in the workshop tomorrow and have a good day.